Okay, I was in the middle of this problem when time ran out on the last video. What we had just found was this FTY was 396.9, or rounding to 3 significant figures, 397. No, actually, I'd written down Newton meters up here. That's incorrect. So I was not solving for a moment. I was solving for the force. I was dividing by down here 2.2 meters, which canceled out that meter there. So that's just newtons. 397 newtons. So that's one piece of the puzzle that's going to get me closer to knowing the tension in the cable and ultimately the force in the hinge as well. So let's keep a note of that, and let's move on to the next slide here. So this was 397. So we can now, we know the angle here, theta is 30 degrees. We know the vertical component is 397. So we should, from this, be able to determine the tension in the cable as well as the horizontal component. And it all just comes from basic trigonometry. If we have a triangle, and the vertical side is 397, and the angle is 30, then what is the other side and the hypotenuse? So looking at this angle, we've got the opposite and hypotenuse, OHO, so we could say sine of 30 equals the opposite side, 397, over the hypotenuse. The hypotenuse in this case, the diagonal, is Ft. That's the tension in the cable. Okay, so Ft is just going to be equal to 397 divided by sine of 30. And so that gives me Ft is equal to 794 newtons. So this is 794 newtons. Now if I wanted to know the x component, okay, again, I can just look at this triangle here. I want to know the adjacent side, knowing the opposite adjacent, TOA. So tangent of 30 equals 397 over the adjacent side, which is FTX. So FTX is equal to 397 divided by tangent of 30. And that is equal to 688 newtons. So that is 688 newtons, FTX. Now if I go back to the previous slide, when I first started off, I had come up with, here we go, a couple things, including this, that the horizontal force in the hinge is equal to the horizontal force in the cable. So that just means, going forward here, that the horizontal force in the hinge, FHX, is also 688 newtons. It's just that it's going to the right while the tension force is going to the left, and those two things will cancel each other out. And finally, to find the vertical hinge force, if we again go back and look at what we've previously calculated, let's take this right here. Okay, and so what we're saying is the vertical hinge force plus half of the tension force minus 519.4 is equal to 0. So I'm gonna make a note of that. Let me write that down. And then we'll move forward back to the slide that we were working on here. Okay, and so let me write that down again. FHY plus 0.5 FT minus 519.4 equals 0. So I know FT. FT, the tension in the cable, is 794. So FHY, I'm just going to start taking these other things to the other side of the equation here. So FHY is equal to, now this negative is going to become a positive, 519.4, and this is going to be a negative 0.5 times 794. So the horizontal force on the hinge is equal to, I'm coming up with 122 newtons. Now, I see down here that because in my original PowerPoint I had solved this problem in a slightly different order and gotten this answer first, I can compare what I'm getting now to what I got then. It's really close. I'm off by a newton. I suspect that's just rounding. After all, this 122 is actually a 122.4, and even then that was based on a rounded number right here. So if you're off by 1 or 2 newtons, that's understandable. That's just comes with the nature of these multi-step problems. So yeah, now this is 122, and if I want to find the FH, the total force in the hinge, I can just use Pythagorean theorem. I've got a vertical leg and a horizontal leg that I know. Okay, I know the vertical is 122. I know the horizontal is 688. And I'm just looking to find the hypotenuse. So if I just take the square root of 122 squared plus 688 squared, that is equal to 699 newtons. So that's the last unknown force here. 699 newtons is the total force acting on the hinge. And I could even, if I wanted to, find the angle, theta, that this force makes. Again, just basically using trigonometry here. We've got the opposite and adjacent, so I can use tangent. So inverse tangent, theta is going to equal the inverse tangent of the opposite, 122, over the adjacent, 688. And so this theta over here on the left side by the hinge is equal to 10.1 degrees. Okay, so let's see if I want to keep going or stop here. I could go forward a little bit. Still got a little bit of time in this video. So an application here to the medical field. The textbook offers a lot of physics applications in the medical field. The fact that the spine is essentially like a column that is held in place with muscles that don't really have a whole lot of moment arm distance, that means that they have a significant amount of tension in them to try to maintain the stability of the back, especially when you bend over. So because you've got a small moment arm distance, it leads to large forces, which can put a lot of stress on your back. Okay, so a little bit here on stability, just the concept of stability. Here, with this ball hanging from a string, gravity is pulling it straight down. The string is pulling it back up. It is in a state of equilibrium. and it can be said to be stable. This is the equilibrium position here. If we apply some other force, some third force here to the side to keep it in this position, it's in equilibrium, but it's not necessarily stable, because if we remove that third force, it's going to swing to the side. So something that is in a state of equilibrium may not necessarily be stable. You could balance a pencil on its tip such that the center of gravity of the pencil is directly over the point that it is balancing on, and it would remain that way unless even the slightest little force from the side pushes it over. Then the equilibrium is upset because the center of gravity is no longer above the point that it's balancing on, and it falls to the side. So it is no longer in a stable state. Okay, so if you tip a refrigerator up on its side, as long as you don't tip it so far, as long as it stays, the center of gravity stays to the inside, looking at the two corners, the footprint of this refrigerator. As long as that center of gravity stays to the left of that corner, it will fall back down and remain stable. Once the center of gravity passes beyond that pivot point, it becomes unstable. This is just another everyday application of physics. If you're carrying a heavy load in one arm, you've, I'm sure, done this before, probably without even thinking about it. You lean to the side. You move your center of gravity further to the right to compensate for the heavier weight on the left side. Those two forces, the force times the distance, the moment arm distance, will cancel out with this moment arm distance and this force. And that's how you're able to stay balanced with this heavy load in one arm, even though you're leaning to the side. Okay, I think that's an ideal stopping point, because we're going to pick up with a new concept starting in section 9.5. We're going to start talking about elasticity, stress, and strain.